Okay, this is video number 4, and I think we left off video number 3 in a little bit of a hurry. Let me get back to it, and then this is the video 4 will be on the bonding in carbon. And first we'll go into why it's bonding to 4, why it has 4 bonds, valency is 4, while it should only bond to 2 based on its electronic structure. And then we'll go into hybridization, okay? And then we'll get into what acetylene is all about, which is exactly where we want to go. Let me go back to the screen. So let's tackle this head on. Video 4, right? Bonding in carbon. So let's say electronic configuration of carbon has 6 electrons, right? 2 are already in the inner shell. So it has 4 electrons in the valence shell. Okay, but 2 of the 4 electrons in the valence shell is paired and should be unavailable, which means carbon should only have 2 electrons available for bonding. In the box notation that we have seen before, you may have seen the box notation. Let me get it here. So what's the box notation for carbon? 1s2, 2s2, 2p2, right? 1s2. That's carbon, right? Six electrons. Filled shell, so only 2 available, so its valence should be 2. It's not, it's 4. So one way they try to explain it is through the concept of hybridization. It's to explain the valence of 4 versus 2. So in order to make 4 bonds out of 2, it's like making, gold out of lead, right? You've got to somehow get four unpaired electrons, which means you have to break this damn thing here, right? So hybridization is nothing but a promotion of one of this 2s electrons into the 2p. So the 1s, nothing happens, still remains as 1s2. The 2s splits, so only 1 left in this. And the 2p has 3 unpaired spins, okay? So out of 1, 2, 3, 4, becomes 1, 2, 3, 4. The spin pair here in the 2s breaks into 2s1, 2p3, right? 2s2, 2p2 becomes 2s1, 2p3. Okay, from here, this explains why carbon should bond to 4 things. Okay, this is hybridization. Okay, this is the split. Hybridization goes a little bit more in that you can have this S mingling with all the 3 P's, or this S to S1 mingling only with the 2 P's and leave 1 free, or the 2s can mingle with only 1 P, leaving the other 2 P orbitals free. Remember, the S orbital is spherical, the P orbital is like a dumbbell, right? You can dumbbell it. This is the Py. This is the Pz, right? And of course, this is the Px. So it's basically, orbitals can look like this, right? So the three P orbitals are in the center is the carbon atom, right? And the S is like this, right? The S is spherical. That's how it's structured. So now the question is 3 ways in which this can mingle or hybridize. 1, the 2s1 mingles with all three 2p orbitals. So 2s1 mingles with all three. Okay, what does that do? That is 2s1 with plus 3p. That's s1p3 or sp3, right? Hybrid orbitals, right? sp3, 1 plus 3 is 4. That is 4 hybrid orbitals. So one carbon has 4 hybrid orbitals, 4 orbitals. The best way to do that, would be to have carbon in the middle. This one's coming at you. This one's going inside the plane of the paper, and let's call it hydrogens attached to 4 hydrogens. So this carbon has 4 bonds in the form of a tetrapod, right? It's a pod. It's a tetrahedral pod. So it has 4 bonds. That's the best way to put 4 bonds in an sp3 orbital. Okay, sp3. Or the 2s1, you doesn't have to mingle with all the 3p, right? Mingles with only 2 of the 2p orbitals. Maybe this one mingles with just this and that. That one's free, leaving the third p orbital untouched. How does that look? So that'll be, that's going to be interesting, like 2s1 plus 2p2, right? This is 2s1 plus 2p3, right? So 2s1 mingles with 2p2, so that's an s1p2, which is an sp2 hybrid orbital, right? So it's 3 bonds, right? S1 plus 2, S1p2 is 3 bonds. In the top one, S1p3 is 4 bonds, right? So you got 3 bonds in an sp2 orbital. The best way to do that would be to, like, like that, right? It's a carbon in the middle, and it's all like this one's going away from you into the paper, this one's coming at you, right? So it's like a flat thingy. But remember, it leaves the other one untouched, right? See, the other one, the p orbital is untouched like this. So it's like a trigonal, right? With the p orbital untouched. That's an sp2 hybrid orbital. The other way it can mingle is the 2s1 mingles with only 1, right? 2p orbital, leaving the other 2 p orbitals untouched. So what is that? So the 2s1 mingles with 2p1, right? Giving you s1p1, which is an sp hybridization, right? S1p1 is an sp hybridized sp orbital. This is 1 plus 1. There's only 2 bonds. So how can you get 2 bonds, right? I mean, it has to be linear, right? Carbon, and let's call that H, right? It's just linear, right? Just 1 bond. It's not a compound, but just leaves 1 bond, right? So where are the other 2 untouched p orbitals? One is the same, it's there, right? This is in the y, say in the y direction. There's another p orbital that is untouched, right? In the z direction. that's that. That's an sp hybridization. Okay. So now how does this work? Suppose there are two carbons. Now, suppose two carbons are bonding, right? One. What is sp3? You got to get two tripods to bond, right? The best way to get two carbons, right? Two tripods to bond. Let's call that, and then that's going into you. That's coming at you. Let's put hydrogens there just for the heck of it. And then that's coming on the plane of the paper, and that's coming out at you. So here is your sp3 with two carbons. That is C2H6 ethane, right? Single bond, right? Now, what about the sp2? Okay, let's look at sp2. Carbon, carbon. We know it's got to be like this, right? Trigonal. So how do we do this? Okay, let's go like this. This is going into you. This is coming at you. That's going into you. This is coming at you, right? It's planar, right? I mean, there's your bond, right? That's that. That's for one carbon. This is for two carbons. So they're bonded, right? Two carbons are bonding. So what about this? This is the untouched p orbital of one. This is the other untouched p orbital of the other carbon. These can bond weakly, right? These can also bond weakly, overlap. How do we say that is CH2 bond CH2, right? That's that. This kind of strange overlap, we put a double bond, right? In sp3, you have CH3 bond CH3, right? That's sp3. This double bond comes from the overlap of the sp2 hybridized carbon where the p orbital is untouched. Okay, that's where the double bond comes from. So when we talk about double bonds, acetylene, polyacetylene, double bond means an overlap of these p orbitals. And in an sp hybridization of two carbons, we know it has to be linear, right? Sp is linear. I just wrote over it. It's linear. So you have carbon, carbon. So obviously it's linear. But it leaves the two p orbitals untouched, right? So how do you so that's one, the same one we saw before, right? That'll overlap just as in this case. But you also have the p orbitals in the z direction untouched. They can also overlap, right? These can overlap. These can overlap in addition to these overlapping. So which leads to HC triple bond CH, right? That's the triple bond, okay, in acetylene gas. Very different from the triple bond we saw for nitrogen, right? Or the double bond for oxygen. Here it's two carbons coming together. There were two nitrogens coming together, right? So I just wanted to leave it off here because we do a lot of acetylene stuff. So I just wanted to go back on the top to see how we started off with the bonding of carbon with four bonds instead of two, and how hybridization explained a little bit. And then we saw how these things can marry. Marry is also called hybridization. The s orbitals can marry all the 3p, or it can marry only two of them, or it can marry only one of them, right? So if it marries all three, it's an sp3, a tetrahedron, 4 bonds, so 4 single bonds. And if it's sp2, it can marry two and leave one free for a pi bond. And if it marries only one, it leaves the other two for another pi bond, so 2 pi bonds. Okay, so basically, this is the first. If you have 3 bonds, I'm going to draw the 3 bonds, right? This is a sigma bond. This is a pi bond. This is the x direction or y direction. This is the z direction. Okay, that's how it is. So these are weaker bonds. These two are weaker bonds because they're just overlapping this way rather than this way, right? Sigma bonds overlap this way. Well, I'm going to stop here. So we'll continue on the next one because it gets too long.